Thank you guys for coming out, spending your afternoon with us. My name's Prakash. This is Matt and Slava, and we all are from a company called Nextdoor. How many people are familiar with Nextdoor? Just quick. Oh, there we go. Man, I did a presentation yesterday, and I did the same question, and like 3/4 of the room was like, Nextdoor, what? So that was a much better start. Thank you, guys. We're going to talk a little bit today about how we rebuilt our data pipeline. We're not going to go into a lot of detail about the data pipeline itself. We're going to talk about some of the component parts and some of the technological decisions that we made. But the key here is we had a legacy data pipeline. It was really important to us, and I'm going to tell you a few ways that we use data in our organization. And then these guys are going to tell you more about some of the problems with that data pipeline and how we replaced it in a serverless way. But first, a little bit about Nextdoor. So we started Nextdoor in the summer of 2010, so it's been about 7 years. We are now in about 80%, actually more than 80% of US neighborhoods. We're also in Germany, the UK, and the Netherlands. And people are using Nextdoor in a wide variety of ways, whether it's finding a babysitter or a plumber or an auto mechanic, reporting and reuniting with a lost pet, reporting crime and safety issues, lots of different ways that people are using it. And in fact, it's used by more than just members today. It started out just being about connecting residents in local communities, but now it's also about connecting them to all of the organizations and constituents in their local community, including local law enforcement, municipal agencies, businesses, and eventually organizations and interests that they share. And again, used by 80% of neighborhoods, we actually have mobile applications and web applications. We're trying to get more people to use our mobile applications because that's a better experience for them. And outside of like Facebook and Twitter, which really pioneered the whole concept around social networking, we're not about self-expression. We're not about connecting on the basis of things that you're necessarily like interested in or that you want to express about yourself. It's really about utility. And so when it comes to building a product like Nextdoor, it's really important that we're able to get feedback from our members. And unlike the early days when we could just go out and talk to our members, because there are only a handful of them, and that's how we started the company, very, very qualitative sort of interviews with our users, we now rely pretty heavily on data and a lot of instrumentation, whether it's analyzing the results of an A/B test or thinking about different signals that we want to integrate into feed personalization or email delivery. It's really, really important. And so today we're going to look at a few of the ways that we use data, and then these guys again are going to talk about the tools that we use to collect that data and pass it along through our pipeline at scale. And so again, data drives a lot of our product decisions at Nextdoor, and what you see here is a sampling of the different ways that we use data, whether it's delivering emails, delivering push notifications, and figuring out which of those are important and urgent for us to notify our members about. And today we're pretty generous about that. Any of you guys that use Nextdoor probably get a lot of emails from us, so sorry about that. We're working on it, though. We're working on it. And then also things like statistics that we display all throughout the site. For example, here you can see that in my neighborhood, which is called Central Fillmore in San Francisco, we show a little counter of what percentage of the neighborhood is actually on the platform based on the number of residences there. Of course, ads are really important to us, and so for anybody that's worked on an ad serving system, you know that there are a lot of signals that you ingest. Some of those are behavioral signals that you have to instrument in the clients to be able to pass down through and use, and so we do that as well. And then of course, A/B tests are really, really important to us. And over time, while this is not exactly to scale, this is representative of the growth in data since we started the company and really started to focus on data almost 4 or 5 years ago to today. We're ingesting over 3 billion events a day. And so it's nothing to shake a stick at, right? There's a lot of stuff in here. And what you're seeing here represents 2/3 of our entire DevOps team, what we call systems infrastructure inside of Nextdoor. And that's on a team of close to 100 engineers. We're starting to grow closer to 100 engineers. And so 2/3 of the team is here right now. So the one guy that's left, I hope everything's going okay. But really, this is by design. And the only way that you can design an organization around this is by relying heavily on automation, on repeatable systems that you can observe and that you have instrumentation around. And really, it's about building robust technologies and being very selective about the things that you run internally and the things that you decide to allow someone else to run, like AWS. Or some of our partners. For example, we use SendGrid for sending email because we don't want to run our own email infrastructure. And so that's what's allowed us to keep our team small and lean. And so I think when we were thinking about our data pipeline, it was really about improving its reliability, designing a system that could scale with very little kind of operational overhead or maintenance or more of these guys. Although, you're probably owed a couple more guys, so sorry about that. But it's really about minimizing the amount of intervention that we need to do manually and relying on automation as much as possible. So Slava's going to talk a little bit more about this real-time data ingestion pipeline, so I'm going to hand this off to him.
All right. Thank you, Prakash. Hello, my name is Slava Markiev, and I'm an engineer on the systems infrastructure team at Nextdoor. My background is in data engineering, and I worked on the data ingestion pipeline that we'll be talking about today. I have a lot of content to get through, and I'd like to ask everyone to hold your questions until the very end. So before getting to the cool new stuff, I want to step back and take a moment to describe where we came from. We ran Apache Flume, which is a distributed, self-hosted streaming service similar to Apache Kafka or AWS-hosted Kinesis streams. Flume served us well for 4 years and scaled up to handle 1.5 billion events per day. Our legacy Flume pipeline consisted of 2 parts, Flume agents and Flume collectors. Agents ran on hosts and collected logs off of servers and forwarded them to a cluster of Flume collectors. From there, the collectors partitioned and forwarded the data in batches to different data sinks. In our case, agents collected syslog and application logs, forwarded them to collectors, and collectors would multiplex that data to S3 and Elasticsearch. The data was made available for real-time consumption in Elasticsearch by developers and product owners. Separately, the data was dumped to S3, where our offline batch ETL workflow would further process the data and act on it. The legacy pipeline worked well for a while, but was susceptible to back pressure, was very rigid in its configuration, and sometimes collectors' buffers became corrupt, making it very hard to recover that data. Additionally, we found that Flume agents were very CPU hungry, which caused issues with mission-critical infrastructure like databases. Finally, it was impossible to dynamically scale this pipeline to handle cyclic load, let alone spikes. I glossed over this, but this type of pipeline is very susceptible to back pressure. So if you run spot nodes, you want to get the data off of those as quick as possible before they're terminated. So if you have large delays upstream in your pipeline, you're potentially going to lose data. So as Prakash mentioned, my team is very small, and we support lots of different product initiatives, as well as general infrastructure usage at Nextdoor. We needed something that would provide the service stability we were looking for, while decrease the operational overhead of running a pipeline. We wanted something that was easy to iterate on and reconfigure, something that would provide better SLAs, and something that was more resilient to influxes of data. Additionally, we wanted to enable data-driven product features that required tighter SLAs. For example, on Nextdoor, we collect clickstream and impression logs through our data pipeline to understand what content is trending upwards in popularity. This data ends up in S3, where we can analyze it to understand which users in a neighborhood still haven't seen a particular piece of content, and write aggregate statistics that influence our push notification triggers. Now, while this type of product feature was technologically possible with our old pipeline, we found that it couldn't deliver a consistent enough SLA to provide a good user experience. So like so many companies today, Nextdoor started in the cloud, and we have been a heavy user of AWS services since. When exploring options for the new pipeline, we naturally looked to AWS to see what services they could offer us. We decided to use these AWS managed offerings to build our new data ingestion pipeline. So quickly going through them, Kinesis Streams allows data to be streamed in batches of events. Lambda is a service where you can upload your own code, and it handles executing it for you. It is able to be linked with data sources like Kinesis Streams, allowing your code to transform incoming data. Kinesis Firehose is similar to Kinesis Streams, but aggregates large batches of events and writes them to S3, hosted Elasticsearch, or Redshift. And lastly, S3 stores the data, making it available for offline processing. The new setup is similar to what we had before. Kinesis agents collect logs off of hosts and send them directly to Kinesis Streams. Our code is executed by Lambda, where it does some data transformation on the incoming logs and sends them to Elasticsearch, and separately to Firehose, where they are dumped to S3. We needed to write a little code to transform the incoming data, making it consumable by downstream processes. Lambda makes it easy to write lightweight processing functions in Node, Python, Java, and C#. However, it's ETL, and there's a lot of boilerplate. Things are constantly being re-implemented, misimplemented, or left unimplemented. So what is ETL? ETL consists of 3 parts. Extract the data by reading from a data source and create a machine-readable object, transform the data in some way, and finally load it somewhere else in a potentially different format. ETL can be thought of as 3 steps, but in reality it consists of a handful of steps. You need to read your data from a data source and be resilient to intermittent failures, deserialize the data from binary form into something you can work with, filter out what you don't need, do some transformations, batch it up, and transport it to a data sink. This entire process requires logging, monitoring, retrying, and error handling. So for the vast majority, the only custom logic you really need is if you require custom data transformations. So we had all the building blocks to make a streaming ETL pipeline with AWS, but we needed to standardize our Lambda code to make it reconfigurable and reusable. What if tomorrow we wanted to ingest logs from ALBs, ELBs, or VPCs? What if we wanted to pipe that data to a BI tool such as Splunk, or join it with another data source? Copy-pasting, tacking on features, or worst case, rewriting from scratch isn't in line with our engineering principles at Nextdoor. Think about how vastly different a function that processes 10,000 events from a stream is from one that processes 10 million events from a file in S3. Consider the implications on compute time, network performance, memory footprint, and a whole host of other things. The business logic for transformation may be the same, but they are hardly the same function. Our solution was creating Bender, an AWS Lambda function written in Java that we could reconfigure and reuse across different pipelines and teams within the company. Bender can be thought of as the skeleton for creating streaming ETL functions on Lambda. The modular design makes it easy to plug in custom code but leverage what has already been built. It comes with a handful of different implementations for each step of the ETL process. The same function could be used regardless of the data source, the transformations, or the data sink. Those things are automatically handled by Bender. Simply write your business logic where it makes sense and create your function configuration. Bender can currently read from Kinesis, S3, and SNS, filter data with regexes or simple string contains, parse it into objects from JSON, or regex patterns, which allows for processing of unstructured data, such as web server logs. We have a growing set of operations to transform the data and wrappers to provide some context as to where that data came from, and what processed it. Finally, Bender can send to a handful of data syncs. If you didn't see a data source or a data sync to your liking, we made it easy to add additional support. A few non-ETL functions to call out are graceful retries, event count and performance reporting, configuration validation, and documentation. I consider the standardization of configuration to be the cornerstone of Bender. It ensures new features get standard configuration and documentation, which is essential in a tool like this. So having touched on what's supported, let's now go over how to configure a Bender Lambda function. Bender is configured via YAML or JSON. I left a few things out of the slide, but let's go through the different parts. The handler section defines the data source. This is the type of Lambda trigger. Bender supports multiple triggers with different data types, but we don't allow mixing different types of triggers. You'll want to use multiple Bender functions for that. Next, we define how to treat data coming from a source. You can have multiple data sources and have them treated differently. Maybe you want the same function handling staging and production, but filter out trace debugging in production. The source regex allows you to filter out streams and S3 paths prior to reading data in case you accidentally added a trigger. And while reading the data, but before further processing it, the regex patterns allow you to filter out records based on their contents. The deserializer instructs Bender how to read the raw data into an object. It's possible to also add schema validation in this step. The list of operations is where you define what transformations to perform on your data. This is your business logic. Maybe you want to rename fields, join with another data source, for example, adding geolocation for logs containing IP addresses, or some other type of mutations. I'll get into what that looks like in a moment. And finally, you can also add complex filter logic here as well. Next, wrappers can add context to your data, such as where it came from, how long it took to process, and what processed it. This can be invaluable when debugging SLA issues. With the example on the right, you can see when the message arrived to Kinesis, when it was processed, and how long it took to process. Next, the serializer writes the object we've been working with back to binary form, getting it ready for transport. And the transporter transmits the data in batches downstream. In this case, Elasticsearch. Lastly, reporters log things like performance metrics for each step, counts of input and output events, and failures. So we've gone over what Bender supports today, how to configure it, and I alluded to earlier that Bender is designed to be easy to extend. So let's add a new operation to transform JSON. Something very simple, like if key exists, replace with value. We start with defining our configuration. We need a key and value configuration properties. The @decorators help with automatic documentation generation and configuration validation. And this is what our YAML configuration will look like. And this is a screenshot of the auto-generated HTML documentation. Every feature in Bender gets this type of documentation. Finally, let's write the basic if payload has key, replace with value. It's just as easy to add additional support for different types of data, as well as different sources and destinations. Bender is available on GitHub and will also be part of the AWS Serverless application repository. If you have questions, we'll do a Q&A at the end or find us after. I'll be handing it off to Matt, who will discuss why we chose AWS Serverless.
Thanks, Lava. So, hi everyone. My name is Matt Weiss, and I've run the systems team at Nextdoor for the last 6 years. So that means that I've had kind of the distinct displeasure of having both designed and run the original data pipeline we talked about earlier. I wanted to spend a bit of time today touching on why we picked the AWS serverless offerings for a new pipeline. New small companies that don't have a lot of data, it might be a really obvious choice. The service is easy to use, and the cost is virtually nothing when you don't have a ton of data. But when you start operating at scale, things change, right? And billions of events a day, I think, is considered at scale. So we hear this kind of the statement all the time. Oh, the cloud is great. But at scale, isn't it more expensive than a real data center? That kind of depends on your definition of cost. So I wanted to walk through the services we use, and I'll tell you a little bit about why we chose each one. At the beginning of the presentation, Prakash told you that we designed our new data pipeline to be easy to scale and have the absolute minimum in operational overhead. Our goal is to build great community for our members, not be great at running complex infrastructure. Frequently, people claim that running your own infrastructure is cheaper than hosted services, but when we compared tools like Kafka to Kinesis, the raw out-of-pocket costs were actually pretty close. More importantly, though, if we ran it ourselves, it would be another tool that our team had to operate, monitor, and scale as the business grew. And we knew from past experience with Flume that we wanted to have as hands-off of a system as possible. We wanted our developers to feel free to instrument as much or as little of the user experience as necessary without being hampered by concerns of breaking the underlying infrastructure. Kinesis gives us streams that are highly flexible, performant, reliable, and scalable. And with tools that AWS has supplied, we can interact with the streams without writing almost any of our own client code. We can even auto-scale the streams as our data patterns change, ensuring that we don't have to manually monitor and scale things up and down when events happen. In the old Flume pipeline model, your servers are always ingesting and forwarding data, and that's the basic Flume design. That generally means that each server has its own local storage where it stores the data as it comes in before the data can be pushed out to your targets. And this makes the whole system really susceptible to backlogs that can take hours and hours to work through. If you pile too much data up on one host, there's really nothing you can do to get the data off that host other than wait for it to go. Newer systems like Apache Kafka and Kinesis both allow you to separate your data ingestion and storage model from your execution layer. In both, you pay the compute overhead, of course, of separating these duties, but now you can scale these two layers separately. The operational benefits of allowing AWS to handle the execution of our function significantly outweigh any cost savings that we might see by running this on our own EC2 instances. Lambda scales up quickly when we need it to. It scales down when we don't. It provides simple management tools for controlling execution and releases and rollbacks and maintenance windows and all the things you'd really want in a solution like this, and we don't have to build or design any of that. So the big performance trade-off, though, that you make when you're using Lambda and Kinesis streams together is that you end up executing your function millions and millions of times and only operating on a very small number of events at a time. And that's sort of the design of Kinesis and Lambda, is to do lots and lots of tiny operations over and over and over again. When your data target can handle this, that model works really well. So if you are pushing to Elasticsearch, which we do, we hit nearly 70,000 events per second going into Elasticsearch without any real problems. However, if your downstream endpoint is S3, for example, and you plan on analyzing your data using Hadoop or Athena or something else, having millions of files that have only a few thousand records in them is really inefficient. And your developers are going to be pretty pissed when you tell them that they have to read 150,000 files to get an hour worth of data. Firehose, actually, as it turns out, is a really great tool for pushing lots of small data chunks, batching them up, and dumping them into S3. And we're able to easily control the batch size, delay, et cetera, And we end up being able to continue to operate a really simple streaming architecture rather than adding in any kind of storage or buffering mechanisms into Bender, which would make it more complicated and more buggy. So I won't spend a ton of time on S3, but it's the gold standard in cloud storage, and it's fast, it's easy to run, it works with all of Amazon services. Newer services like Athena make it really easy to do direct analysis on your data in S3. And there's such a natural fit that when we were developing Bender late last year, the Athena team even reached out to us to have us trial their product with Bender because those two fit really well together. One thing I'll mention though is S3 is not only good for your long-term storage, but it's really great as a short-term storage location. As I mentioned before, we use Firehose to dump a near raw stream of our Kinesis data into a temporary S3 bucket. And then from there, SNS notifications trigger Bender to pick up these files, process them, pick up the files and process them. Bender's able to do all of the complex key manipulation and partition the data out the way we want, and that keeps our downstream data teams pretty happy and keeps things working well. This is fun. So I wanted to put this into perspective a little bit. We talked about the kinds of problems that could happen with our old pipeline, but we didn't really give you anything concrete. What kinds of issues were we really seeing? So this is how bad it was at the end. This is a graph of the old pipeline in its final few months of service. The y-axis here is a percentage of fill, and anytime it's filled up at all, that's bad. If it's filled up a couple of percent, things can recover on their own generally. If it's filled up beyond 10 or 15%, you start running into real problems. So we had weeks upon weeks of regular outages and delays, and most of these delays lasted hours to recover. The one really big spike actually represented data loss for us because we actually filled the pipeline up and couldn't stuff anything else into it. So during these times, our product and engineering teams were partially or completely blind. They couldn't develop the product. And actually, in some cases, user-facing portions of the website were showing stale data. So what did it look like on the new pipeline for the same time frame? So to be clear, we're looking at a different metric. Kinesis doesn't have a concept of fill percentage, but rather there's a metric that indicates how far behind now your function is operating. So effectively, it's a direct measure of how quickly your function is able to keep up with the incoming data flow. Just to remind you, this is the same time frame as the other graph, and the data volumes were exactly the same. We were duplicating the data into the old pipeline and the new pipeline. The largest spike we have here is less than a minute, and that was probably even self-inflicted somehow. So I can't say it's been perfect the whole time, but it's been significantly better than the previous graph. So by the time we had fully switched over to the Kinesis pipeline, our Flume pipeline was failing and dropping events. And that's at nearly half the data load we currently support. So to that end, I can't tell you how much it would have cost to actually run the old pipeline at our current scale. Significant architectural changes would have had to happen. That said, on paper, the old pipeline was cheaper on a per billion events sent basis. But that doesn't take into account the business impacts of the outages we were dealing with or the engineering time that was required to sort of maintain and run the old system and deal with these outages. The old pipeline was delaying product decisions, distracting the systems team, frustrating dozens of engineers, and the new pipeline works so smoothly that I think most of our engineers don't know it exists anymore. So on paper, at scale, the cloud may look more expensive, but when you start looking at the business impacts and the distractions that running it yourself can create, it's a different game. So wanted to take you guys through a quick tour of a real pipeline that we created using Bender. This is a really simple pipeline. We have a basic flow of CloudTrail events that go into an AWS-hosted Elasticsearch service. In this example, we built the entire pipeline from start to finish in a single CloudFormation stack. And the stack's actually going to be available for you to download at the end of the presentation. The way this works is that we have CloudTrail that writes files into an S3 bucket. From there, the S3 bucket publishes notifications to a topic. The topic in turn triggers the execution of our Bender function. And then Bender uses an IAM role to read the original data files from S3, process the data, and finally ship them into Elasticsearch. So I'll walk through some of the individual components here. If you're not already familiar with it, AWS CloudTrail allows you to log every API action taken in your account, either by you or on your behalf. You can configure unique trails per region, or you can configure one trail for all of your regions. Here you can see that we've got one trail for kind of all regions going into an S3 bucket. And if we look at the S3 bucket, we can see all the files that CloudTrail is uploading. And these files are dumped every couple of minutes. And then S3 fires off a notification to our function. The trick here is that each of these files, while being 60K and 38K and meaty, each file is one line long. It's a single JSON object with an array in it, and in the array is all of the actual CloudTrail records. So that makes processing this data with most tools just pretty obnoxious. You certainly can't pipe it directly into Elasticsearch. When we go and we look at the Lambda console, we can see how frequently our function is running, how long it takes on average, min, max, durations, all that. You can modify your triggers, add more triggers, et cetera. And I'll note that Lambda doesn't really force you to design your triggers in any particular way. Slava alluded to this earlier in that you can have one function that is triggered by dozens of different types of sources or just dozens of different of the same source, so Kinesis, streams, SNS notifications, et cetera. We've mirrored most of this into the Bender configuration. We do limit you to one type of source, but not one source, and you can treat different sources differently. So one of the goals of this particular demo, right, was to have a system that was completely managed by AWS. So here we're using the hosted Elasticsearch service as our target. CloudFormation makes these things really easy to launch and run, and if you've ever run Elasticsearch, you know that even the smallest clusters generally require a little bit of hand-holding and monitoring, so using a hosted solution here is great for this. Bender can push, of course, to any Elasticsearch cluster, but this made it really easy. So let's see. Here's the end product. We have a Kibana dashboard served on an AWS-managed Elasticsearch cluster with data populated by a completely serverless ETL framework. While technically there are servers here, from our perspective, this is a serverless pipeline because we aren't managing any EC2 instances for it. So why did I use this example, right? Why did I do this instead of something more product-focused? CloudTrail logs are one of those great tools that AWS provides, but they expect you to do some work to get value out of them. And there's a number of different reasons why you might want to go through them. Perhaps you're trying to figure out why you're being throttled by Route 53, or maybe you have concerns about a security breach and you want to find out which engineer flipped the public bid on an S3 bucket and leaked a few million social security numbers. Whatever the reason.
We haven't done that.
As far as I know.
No, that's never happened.
But whatever the reason, right, parsing these logs is hard, and especially since, as I mentioned, their one-line format makes things a little more difficult. So just by logging into the main interface, we can quickly see a histogram of API calls and a few of the most recently recorded calls. The data is a little dense here, but if you look carefully, you can see that Bender already did some work. All the key names are in bold, and Bender has appended the type of data to the key name, ensuring that in Elasticsearch, we don't have any schema conflicts. If we dig into a single event, we can see the service, region, event type, details about the client. You can see who's making the calls, and you can even get the individual request parameters. And so from here, you could see how if you knew what you were looking for, it would be pretty easy to start searching through and trace down the actions of a particular user or role or account in your system. But what if you don't know what you're looking for? So this is where a dashboard could come in really handy. This is a quick, simple dashboard that gives you a few views and kind of the different types of API calls, service by type, by user, over a period of time. And sort of from this board, you could start filtering for what you care about. And as you can see here, the vast majority of our calls are from Cloud Health and Amazon and Datadog, and so maybe we want to filter those out. So now, as we filter that out, we start to see kind of a more expected pattern among the users in our account. And in our environment, we use Okta to delegate short-term access to our Amazon resources through SAML assertions and IAM roles. And so maybe in this account, we don't expect to see very many API calls from that particular role. So we zoom in on this particular role, and we can start to see what they're up to. We see some describe calls, which are probably not that worrisome. But you also see a stop task and a change resource record sets call. And if this is your production account, maybe that's worrisome, right? Maybe someone's messing with your DNS. Now, if we care about those calls, maybe we want to find out where they came from. So Amazon embeds the source IP into all of the CloudTrail records. So what can we do here? So using a Bender operator, we're able to enrich the CloudTrail data with the GeoIP database as it flows through the pipeline. This makes it really simple to plot the location of all the API calls on a map and look for outliers. Now, our office is in San Francisco, so the big red dot makes a ton of sense. But maybe the other blue dots, especially down in Santa Clara, don't make that much sense for us. So we're able to select the area using some mapping tools, and that automatically creates some latitude and longitude filters for us. And then we can use that filter to go back into the search view and look at the individual calls that are being made. Apparently, I like to work remotely, so those API calls were actually me, probably working out of a Starbucks somewhere. But using Bender to enrich the data as it goes through the pipeline is a really efficient way of adding sort of relevant metadata without adding a whole processing job down the road. You could see how this might be useful with other data sources, perhaps looking for where ad purchases are coming from and spotting concerning trends. And so the pipeline we've demoed here is actually a real pipeline we run. As Prakash and Slava mentioned, right, we run a much larger pipeline for all of our logs and events that we transform into business dashboards and product decisions, and even to customize the Nextdoor experience for each of our users, but it doesn't mean it's our only pipeline. As you grow, you may find that you have needs for many different pipelines, each with their own data sources, transformations, and outputs that are required to make the data usable. Your IT team might want to run a pipeline like this to keep a close eye on security events, or your engineers might want to run a pipeline to track ALB and ELB request logs, or your product might need to be able to take Kinesis stream events and pipe them into API endpoints. Rather than rebuilding the wheel each time, using a single tool that has all the boilerplate behaviors built in provides serious leverage and helps your teams focus on the real work that they need to get done. So, just a reminder, the system seems very small. We've talked about that a few times. And we manage hundreds of servers and billions of events daily. And in order to do that, we have to automate everything. And we operate only the things we really, really have to operate. So Lambda, Kinesis, Firehose, and S3 have allowed us to take this sort of traditionally finicky piece of infrastructure to a service that scales and handles failures automatically. Building Bender has given us a single ETL tool that we leverage across multiple teams and products, rather than building custom tools each time a need comes up. Our reliability has gone up dramatically, and the effort we spend on running this stuff now is near zero. So we appreciate everyone coming out today. We're open to Q&A now. And of course, you can always talk to us after. And, you know, we have jobs. So, thank you.
You guys have any questions?
Yep. In the blue? So the question was, correct me if I get this right or wrong. The question was, are we having problems with file sizes on S3 downstream? After Firehose. No, we don't generally have that problem. Firehose limits the file sizes appropriately to certain maxes that they have, and we just generally use their max. And then when Bender picks those files up, it's partitioning just that one file at a time. And so we just end up with smaller files after that.
You alluded to some implementation problems in the new pipeline. Can you care to go over some of those?
Sure. So I think the question was, what kinds of problems have we had with the new pipeline?
Well, not necessarily
I'll give you an example of the most recent one. We end up, now that we have this pipeline.
Restate the question.
All right, sorry. So the question was, what kinds of problems have we had moving to this new pipeline? And a recent example is we had a 20-minute sort of mysterious blockage of data going into Kinesis. And that backed up on our servers, and as we mentioned, we run spot machines, and that meant that there was this window of some amount of panic as we tried to figure out what was happening. It resolved itself, and everything flowed through quickly after that, and it's dramatically better than the types of problems we'd had before, but it still can happen, absolutely.
Right. I think to add, the biggest limitation I've had with kind of dealing with Lambda is, for instance, our functions get executed like 25 to 30 million times a day. So if there's a failure, CloudWatch logs are very, very hard to look through. And I think that's, as we have more teams start to use Bender or other Lambda functions, because we really pioneered that at the company, is we need to think about how we collect that log data. But that's not too dissimilar from like if you run Flume or Kafka or whatever, if it generates logs, I don't know if you want to like kind of send it back into itself.
Yeah.
Actually,
Okay. Yeah. Oh, you first.
If that's the part, what kind of error handling did you have to put in on the Lambda side, specifically with retry if the invocations fail?
Repeat the question.
Right. So the question was, what kind of error handling did we need to put in to our Lambda function? So, for example, Elasticsearch can sometimes be backed up a little bit. And if you're making multiple API calls to Elasticsearch, you're not guaranteed that you hit the same nodes. So even if we retry like 3 times within the function, that is much better if we can retry in batches, in small batches, rather than retrying in like 10,000 events. Or at one point, we decided to like use S3 files directly to Elasticsearch, and it kind of keeled over and died.
Yeah.
Would you persist those messages in like a DynamoDB or just done in the SQL?
No, so this is important, and this is one of the things we like about this infrastructure, but took us a little while to sort of understand the impacts of. You just fail the function, and Amazon will rerun it for you on their own. And so there's actually, because you're being billed per millisecond in Lambda, if you sit there and you say, well, retry, and then back off for 5 seconds and retry again, and back off for 10 seconds and retry again, now you're wasting time where you're being billed for it. Your function's running for that whole time, but it's sitting idle. In most cases, we've actually tuned most of our retries down to 1 or 2, and then we let the function fail. Now, that's not that's true when you're operating off Kinesis streams. If you're operating off of an SNS notification from an S3 bucket, then your sort of rules change a little bit. Sorry.
You were in multiple regions. I was wondering how you deal with visibility across the regions, or if you keep everything completely segregated, so you know where the data is.
So the question was, do we keep everything separated in individual regions, or do we group it all into one, right? And so we pipe all of our data into one region today. So while we run the website out of many regions, we have one area where we do our BI and analysis, and so we pipe it all there.
So just as a rule of thumb, like when you have been trying to tune for performance, did you find it better to try to maximize the throughput on your Kinesis streams by minimizing shards, or do you find it better to just go wildly overboard by increasing the number of shards that you can execute more lambdas at once?
Yeah.
Slava had a really good time with that.
Yes, I spent a lot of time on the phone with engineers. I think it's a double-edged sword, if you will. I would say it depends on your final destination, right? If you're hitting something that's like an API or a service like Elasticsearch, it can only handle so many requests at a time, right? Alternatively, it can only handle like so much data per request. So there is a balancing act to perform. So we found that if we tune down the number of shards, for our case for Elasticsearch, it was much better for it. And then, what was I going to say?
Well, going into Firehose, for example, it doesn't seem to matter. Firehose just gobbles data up as fast as it can. But Elasticsearch, we absolutely ran into an issue where we said, why is the cluster performing so badly? We don't understand. It worked fine and the data volume was the same, but it was the number, we had almost doubled the number of executions of the Lambda function, which doubled the number of sort of simultaneous puts into the cluster. So it's a trade-off.
Right. And I think just to add to that is if you have too much capacity with your shards, that could also potentially be an issue because then you're kind of wasting execution time because your function may just get one single record that it's handling. And that's just expensive, so it's a balancing act, right?
Sorry.
So how do you change the file size of, when you are putting into S3, if you get this small file, there will be too much full operations that you will be spending cost for. So how do you change the size, what is the right size so that you put into S3 so that the cost on putting the file on S3 is optimized?
Why don't you start?
Well, so I think the question was how do we tune our S3 puts at the end of the day so that when we are putting files down, we're putting reasonably sized files down in S3. And as I mentioned earlier, we use Firehose to do some batching, and so that helps. And so we use the max batch sizes for Firehose. So it's like, 300 seconds or
128 megs of compressed data.
Or 128 megs of compressed data. And when our function picks that 128 meg file up, it may split that into 3 files, 30 megs each or 40 megs each, or it might split it into 50. And we don't really optimize for that. That's the long-winded version of saying we don't really pay that much attention to it. In the cases where we are creating a very small file with very few records, we generally just don't have that many of those records in the first place. So the downstream impacts are not that significant.
Another question is that say if someone is thinking about using EMR for the data aggregation and while you are using storing serverless concept, so what are the problems you think with EMR?
Well, I think to rephrase the question, why not use EMR for this? Well, that's just another piece of infrastructure that you need to manage and operate and have alarms on, and it's, I think, relatively complicated, right? Now, that being said, we do use Hadoop and Hive and Tez on our data team separately, but that's a dedicated team that manages those resources.
Yeah, I think maybe another way to think about it is that there's clearly a business use case for something like EMR. In our case, we use a third-party product called Scalable. But if you think about this as transporting data around, really, so it's a transportation mechanism as opposed to a true analysis sort of engine, that's kind of how we created some differentiation for the roles in the infrastructure, which is we need an efficient platform to move data into an eventual data store that we can then analyze. And it may be that we use extensions of this to do things that are later more kind of real-timey or things like that, but we haven't yet found any use cases that sort of serve that, so.
And also, I'll point out that by creating a small function that does sort of the same thing over and over again, it's just an easier system to build and test and extend. And we mentioned this briefly in there where we have support for Sumo Logic and Splunk and Scalar as outputs and as well as sort of generic HTTP endpoints. Literally, like being able to bolt those on was a matter of like an hour of work in each case. And being able to do that on a very small, tightly controlled platform where you can you can run it all and test it all locally on your laptop is pretty valuable.
Do you have use cases where you have tables preserve ordering of the events?
So the question was, do we have any use cases where we need to preserve ordering? So no, we don't. That's not, well, okay. Elasticsearch preserves ordering in the sense that we tell it what the time field is when we're inserting the data. And so that's some semblance of ordering. We actually, Bender can actually process and find the timestamp field and do some parsing, and then when you set your schema up in Elasticsearch, you can sort of tell it where that timestamp field is going to be. But generally speaking, Kinesis is not an ordered system, right? Once you go beyond one shard, it's sort of unordered. So to that sense, no. Sorry, yes. So the question was, for sort of retriable transient failures, you let Amazon rerun the function, but for fatal exceptions, what do we do? A good example is if you have, say, a bad schema in Elasticsearch, and so now you can't push data at all. There have been times where we've swallowed those and figured it out later. And then I think now we take more of an approach of, let it break the pipeline, and we get alerted very quickly when things back up, and we can start going. So by break, I mean just fail, and if all the functions start failing, then the metric I showed you guys earlier, the sort of iterator age of the function, how far behind now the function is, very quickly ramps up, and it's usually really easy to see in that pattern, like, oh, it's perfectly up and to the right. It's not, it's not waving in any way. So that's usually a good indication that you've completely broken some downstream endpoint.
And I would just add one thing, which is I think it is a little bit use case dependent, because in some cases we can respond to failures like that by republishing data. And in other cases, it's not so easy to go back to the point of failure and figure out exactly what was coming through. And in those cases, we have to be careful, right? And so far we haven't had anything fatal happen. And I wouldn't say that we have the best, sort of most robust answer to this. Some of it goes back, someone had mentioned, like, do you do like cyclical stuff, like republish something back through, and even to log something like that. This is our log pipeline, right? So it's sort of a weird kind of like recursive thing that happens, right? Another thing that I think could be useful in this situation is if you have distinct platforms for for example, we use Datadog, right? And Datadog is sort of our metrics platform, so we can say failure, 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 failure over there, and that's informative, and that has kind of an alerting system. And over here, it's really our delivery pipeline into our eventual data stores. And so I think there's some room for us to use both of those systems to kind of keep track of one another a little bit. So.
Right, just to add, I think it really depends on what your source trigger is, right? If it's Kinesis, and we built it in where if there is a failure, you can just swallow it and just the function will keep going. But in our case, we just want to stop what that shard is on and just keep retrying. Now the caveat is it's going to back up, but we have 24 hours to recover that, or configurable up to 7 days, right? So we're not going to lose data.
Slightly better than the old pipeline where we usually had about 40 minutes before, if things were still backed up, then it would go south and it would be backed up for like 8 or 10 hours. So there was another question over here. Yes?
Yeah, I was just going to say, like, in the case that, like, Kinesis has a longer term outage, or like we have a long-term outage, which has happened, do you guys have any plans to, like, fall back, or we could fall back to like another region?
So the question was, if there's a long-term outage, sort of what's the plan? And it does depend a little bit on where that outage is. So if there's a long-term Lambda outage, which that's definitely happened a few times in the last 6 months, I think generally our plan is, right now, is to just let it be, and Amazon's going to work on recovering it faster than we could make any major changes. And as we said, you have at least 24 hours of sort of data hold in Kinesis, and so we don't have to worry about it sort of filling up in that sense. If your problem is at the Kinesis level, it depends on how quickly your machines come and go. On the machines, on some of our machines, like data store machines, we could let it back up for days, and it wouldn't be that big a deal. But we run ECS and Docker, and some of our machines live for an hour or less. So in that case, like our sort of standard procedure is to stop any scaling activities that we can control, and then work as quickly as we can to figure out with Amazon what's going on. If we had to, it would not be difficult to roll out a change to just change the stream target. But there are some consequences of doing that. So we haven't had to do anything like that yet. Yes?
Obviously, some of the advantages of serverless is highly scalable, highly available, but one of my favorite concerns is cost. How does cost scale? Obviously, you're at 3 million a day, and eventually 4, 5, 6. What is the cost of that?
So the question was a little more direct around what is the cost impact of doing this, all in Amazon serverless environment rather than running it yourself. And I had a slide actually, and I removed it, where I actually worked out the actual per billion event cost, and I didn't think Amazon would want me to put that up here. It was reasonably more expensive, 30-40% more expensive. Now, again, it was really, really hard for us to look at the data, though, and decide if that was accurate, because the old pipeline was losing events. And to some extent, that might have been us sort of trying to operate the old pipeline too efficiently, because when you are managing your individual resources, your individual servers, I think you have a tendency to look at them and go, well, why is this machine running at 5%? Why can't I run it at 70%, right? And the answer there is that on these traditional pipelines, you can't really scale them up and down very easily. So you sort of have to always build for what scale limit you want to be able to hit. So yeah, it's definitely more expensive, no question. But the trade-off for us is that when we have big spikes, we don't notice them. When our data patterns just change over time, we don't really notice them. The only place we actually notice when our developers have suddenly turned the trace debugging, the trace bit on some application, is in Elasticsearch, where we still have to sort of manage that to our max capacity, and that's kind of our early canary to tell when something's happened. But no, it's a trade-off.
The other thing I would say, at kind of the highest level, when we think about our infrastructure costs and we sort of itemize those, we're always stack ranking where are we spending the most money, are we doing that responsibly and efficiently, and what are we trading off in terms of what we get for that money that we spend, right? So as an example, we mentioned we use some third-party providers for things like email infrastructure and other sorts of stuff. And I think it's a very similar, it's a similar process, right? I don't know that we eventually get to the same outcomes, but as things start to bubble up as larger expenses, then clearly we take a much closer look at it. In this particular case, there was an old framework that we used at Google for thinking, this is back like 10 years ago, for thinking about the opportunity cost of an engineer. And the opportunity cost for one engineer was something like $1 million or something like that. And that's basically how much value could one engineer deliver for the company. And so what's the threshold at which you trade them off to do something that you could otherwise sort of, throw something else at, right? Throw a hosted solution at. So for us, we kind of keep that in our mind as well.
That was actually a follow-up question. If you consider, since your team's obviously pretty small,
Yeah.
you might be paying more for infrastructure than paying less for engineering.
Yeah, we think about it all the time. We think about it all the time, and it's kind of a long-term versus short-term decision as well. So,
Yeah.
I think last one probably here.
Yeah.
These guys here? They are responsible for everything that represents kind of infrastructure in the company. So anything involving the codification, deployment, and provisioning of infrastructure that's used by all the teams, resides in these two plus one other person's capable hands.
The second part was, do you consider other cloud vendors before deciding to go forward with AWS on this?
We've been AWS customers now since 2008. So that includes the company that we started before Nextdoor. We've been pretty happy with them, and I think as you start to continue your relationship with AWS, they afford you, different benefits that help you kind of stay in. And as you start to use more and more of the services, then it's really hard to switch. So we have not really given serious thought to switching.
Yeah. So I think our time's up, but
Yep.
but thank you, everyone. We'll hang
Thanks, guys.
around
We're
and we
around
can
if you have
chat
other questions.
outside.